Okay, lab this week is what?
You don't have one.
Okay, no lab this week. No class on Friday? Okay. Next week in lab, I think, is due your data table. Is that right? When you come to lab next week. Any questions about lab? Okay, we have 3 handouts. Nomenclature by video. We left off with conversion of carboxylic acids to acid chlorides. And we did mechanism there. Any questions about that mechanism? Okay, B, conversion to esters. Well, what was A? What are we under if we're doing A and B? Reactions of carboxylic acids. Okay, second reaction is conversion to esters. Okay. And the green, we can see what we did first. Acids, acid chloride. Most common reagent to do that is what? Diamond chloride, yeah? We did that, yeah? Okay, we're doing all of these. You need to put all your reagents on there. You've already done that, started that? Okay, Fischer Esterification. If you take a carboxylic acid with an alcohol and H plus catalyst, you can get the ester plus water. And if you star the oxygen of the alcohol, it's now that. One of these oxygens here becomes water. Okay? So one of these is lost. This oxygen becomes bonded to carbonyl here. Ultimately, these oxygens are going to become equivalent in the mechanism. Example, we take benzoic acid, take ethanol, and treat it with an acid catalyst. We can get this ethyl ester. Now this is paratoluene sulfonic acid. We'll talk about that. But it's an H plus catalyst. All right. And I think this is the first time we've done this. We'll do this plenty of times going forward, and you'll do this 1,000 times in biochemistry. But you won't do it mechanistically. They'll just show you protonating. They're like, what happened? Yeah, okay. Well, what happens is, if you have H+, we can protonate the carbonyl. Protonation of carbonyl. Very important to understand what we're doing here and how common this is. This makes the carbonyl more electrophilic. More reactive towards the nucleophile. The oxygen is pulling, electronegative, yeah? Well, here the oxygen pulls even more because it's positive. We made it positive, we made it mad. So it's like carbon, you got to give me some electrons. Pulling. protonation of the carbonyl makes it more electrophilic. We will do this many, many times. Now the ethanol here, which is a weak nucleophile, these electrons will add to carbonyl, and these electrons will get pushed up where oxygen wants them. I'm going to draw this out with bonds so we can see here. Of course, we don't work with condensed structures and mechanisms. Some of you need to understand that in terms of your mechanisms on quizzes and tests. Ethanol adds electrons up, and so this becomes what up here? Yeah, it becomes OH. At this point, see how these OHs are equivalent?
Mm.
Now at this point, we want to lose one of these OHs. That's what we want to do. Which one do you want to lose?
Doesn't matter.
It don't matter. Proton transfer. This oxygen is holding a proton. It looks like H3O+. We can do proton transfer. Transfer the proton from this oxygen to one of these. Which one would you like to transfer it to, top or bottom, Megan? Bottom one, we can do that. Actually, I'd rather transfer it to the top one, so I know I asked you. The reason is because I want you to see that the top oxygen can be lost as water just as readily as the bottom oxygen. Okay? I'm going to transfer it to any of them. They're all in equilibrium. Transfer it to the top one. Proton transfer, have we done that before? Have we talked about that before?
Yes.
More importantly, have you convinced yourself what it is? Are you going to continue to work on understanding what it is? Proton transfer from one oxygen to the other, like a hot potato. I'm not going to show a mechanism for that. We talked about that before. It's usually between different molecules, intermolecular. We can just call it H+ transfer. Now, this oxygen is protonated, and it can be a leaving group. How do you make oxygen a better leaving group? Typically protonated, make it positive. Now, what are we trying to do here? We want to have a carbonyl and an O-ethyl. Well, here's the O-ethyl. We need to make a carbonyl. We're going to make it right here. And guess what? Anytime you can make a pi bond and kick off a leaving group, that's easy to do. Have we said that before? We will say it many more times. There you go. We're set up to do that. What does this give? I'm going to kind of move things up a little bit, okay? Double bond to oxygen. There's an H here. We don't magically lose H's. The oxygen's now positive, and we have what? An O ethyl. What do we need to do to get home? Something needs to take the H. What was the minus over here that can take the H?
Catalyst.
Do what?
Our catalyst.
Do what? Well, specifically, what was it? Tosylate. What is a tosylate? These electrons take H, these electrons stay behind. Yeah. And that's going to reform what? We're going to reform the para-toluene sulfonic acid. This is PTSOH. Okay. First off, it's para. It's called the methyl is para. That's why it's called para-toluene sulfonic acid. Of course, when we first looked at it, I did like TOS, right? Like tosyl chloride. We use tosyl chloride. You may see this written as PTS. Okay, it's the same thing. Tosyl chloride. If that's a Cl, that's tosyl chloride. If it's an OH, it's tosyl acid, commonly called para-toluene sulfonic acid. Okay. Where do we produce water at? Right here. Right here. There's the water that we produced. And this oxygen here is now that oxygen there, like we said, yeah? This is called a Fischer Esterification, named after a chemist. One of the top 10 reactions in organic chemistry. Converting an acid, carboxylic acid, to an ester. This is a true equilibrium reaction. It has to be driven one side. How do you drive this reaction to the right, to the product? To the ester, plus water, okay? Usually we just show the organic product, but any Fischer esterification, ester plus water, right? How do you drive this reaction to the right? It can be driven to the right or to the left. How would you drive it to the right? Yara?
You would need to have a less acidic acid on the outside. Because it goes...
There's only one acid up here, para-toluene sulfonic acid. Not an acid-base reaction. It's an esterification. Do what? I just can't hear you.
Like have a lot of your reactants.
A lot of the reactants. How is that going to drive it to the right? So you're saying instead of using 2 grams of each, to use 8 grams of each? And that would drive it to the right? No, there's no difference here. So you're saying a large-scale reaction is driven to the right, where a small-scale reaction is not? No, they're the same.
If you have excess of your ethanol in your tosyl acid, though, doesn't it drive it that direction, even if you don't have I mean, if you change all of your amounts equally of your reagents and your reactants and stuff, then it is the same, but if you
Correct.
have,
So you recognize that?
right, so if you have, like, say you have 2 grams of your starting carboxylic acid and you have excess amounts of ethanol and your tosyl acid, will that drive it then to?
Yeah. And I call these grams, but really we work in moles.
Right.
But these can be converted to moles. Yes, we can use excess of one of the reactants. Which one would you want to use excess of? Typically, you would use excess of the alcohol. That way, the carboxylic acid is totally consumed. Okay? All right? Excess. Excess of the alcohol. And that will push it to the right. That's one way. And because of that, you would only use an excess alcohol if you can get rid of it at the end. Okay? Alcohols that you can get rid of at the end are going to be small alcohols like methanol and ethanol. At the end, you can just rotavap them off. If it's a huge alcohol that's non-volatile, you can't rotavap it off. You're going to be stuck with a huge excess, and you're going to be like, uh-oh, I can't get rid of it. Typically, with the Fischer Esterification, we use small alcohols, methanol or ethanol most common. You can use a couple other small alcohols because you can get rid of the excess at the end. The excess, as Le Chatelet told us, will drive the reaction to the right. Yes, it's a common way to drive it. What would be another way to drive the reaction to the right? Instead of using excess of one of the starting materials, not both, remove the product. It's actually difficult to remove the product. How would you remove the product? How would you remove the product from the reaction class in lab?
While
Or
it's still
really,
reacting?
what you need to remove from is from the equilibrium. You don't actually have to remove it from the flask. Okay, so how can we remove the product from the equilibrium? Which product are we talking about? Knock it out of solution? Okay. Maybe if it would precipitate, it would be removed from the equilibrium, yes. That's going to depend on the nature of the ester. Most common way is not to remove the ester, but to remove water. Well, it's not the best way. The best way is to use excess of the alcohol. Another way to drive it to the right is to remove one of the products. And if we remove water, how could we remove water from the reaction? You could evaporate it out and do the reaction at 100 degrees. As it's formed, the water would boil out. But can you do that?
No.
Why not?
The
If you're using ethanol to make an ethyl ester and you're using ethanol, ethanol has a boiling point of about 80. If you try to boil the water out at 100, the ethanol will boil out first. We'll mention that again later in the course. You could include maybe a drying agent, and as the water is formed, it's sort of chemically dried somehow. Okay? In the end, the most common, you need to think about Le Chatelet, how to derive reactions. Hopefully you've discussed all that in Gen Chem, right? Various ways. Okay? The most common way is to use excess alcohol, and typically use a small alcohol because of the reasons I said. Okay. It's an equilibrium because every step up here is completely reversible. That is, if we had an ester, could we protonate the carbonyl? Sure, why not? We protonated the carbonyl, the acid, why not protonate the carbonyl? Now we get back here. And you get back here, could water add to the carbonyl? Yes, and that would give here. And at this point, could you transfer a proton from this oxygen to this oxygen? Yes, why not? At this point, could you not make pi bond and kick off protonated oxygen? You'd be kicking off the ethanol. And you would get this. And once you kick off the ethanol, could you just remove proton and go back to neutral? Yes. Completely reversible. It's a complete equilibrium. You have to drive it one way or the other. How would you drive this reaction the other way? How would you go from ester to acid, which can be done? How would you drive it the other way, the reverse direction? Do it.
If you heat it up, the ethanol would dissolve, right, evaporate, so it would push
Heated, evaporate out the ethanol. Possibly, yeah. In practice, though, there's a better way. What's another way to do it? Theoretically, yes, that's right. What's another way, though? What's another theoretical way? We'll remove the product. What's another way? Add a starting material. What's the starting material to over here? Going this way. Water. If you add water, it's going to push it the other way. Not remove water, okay? So we would need water and acid catalyst. That sounds like what? H3O plus. Isn't that water and acid catalyst? Water and acid catalyst will do what? Convert an ester to the carboxylic acid. We call that hydrolysis because we're reacting with water. And if we look at the flow chart here, the ester's in the middle. What do we say would happen with anything in the middle, an ester, if we treated it with H3O plus? We go back to what? Riley? Carboxylic acid. Okay? Fischer Esterification, equilibrium, how to drive it. One way making esters, the other way to make carboxylic acid. Hydrolysis of esters to carboxylic acid, common reaction. What's another way to make an ester? By the way, why would you use paratoluene sulfonic acid? Why is that a common acid to use here? What other acids could you use? You use a strong acid to protonate a carbonyl. What other acid? H2SO4. Why is paratoluene sulfonic acid better than H2SO4? H2SO4 is an aqueous acid. If you want to go that way, is water going to help you go that way?
No.
So don't use an aqueous acid. Because when you add in your acid, you're also adding in water. You'd rather use a dry acid. And paratoluene sulfonic acid is much more dry. It's considered a dry acid. It's often hydrated. It's considered a dry acid. A dry acid is better, you agree? You don't want to be adding water when you want to add your acid. By the way, this acid is also a solid. The solids are more convenient than liquids. If you drop a bottle of sulfuric acid, you're going to have a mess. If you drop a bottle of this, you can get out the broom and sweep it up. So, just another side point. Why that acid is sort of common. I don't think we've ever used it before as a strong acid, have we? We usually use sulfuric acid or maybe HCl. Okay, another way to make an ester is by alkylation of the carboxylate anion. You take carboxylic acid, treat with base, What type of base could we use to deprotonate this? Acid-base chemistry. Like sodium hydroxide? Or triethylamine? Okay. And if we're going to show a mechanism, we need to show bonds. Okay. Some of you on test are just throwing an arrow at a reagent. That's not sufficient. Okay. I usually circle it or something. I can't explain every single thing. You should have been tuned into this when we first looked at mechanisms in Organic 1. Okay. Detail. We need bonds. Okay. And so I would want to draw in a bond here so I can then triethylamine. What is that? Nitrogen with 3 ethers. And these electrons can take the H, these electrons stay behind, and that would give carboxylate anion, right? Now if we throw in some type of alkyl group for the leaving group, what can happen next? This can come in here and do that. What does that do? It gives product, right? That's SN2. That's just a good old SN2 reaction, and we saw that same exact reaction in Organic 1. Same exact reaction I showed you in Organic 1. But we're converting a carboxylic acid to an ester. By how? Alkylation. Now in this case, this oxygen is still that oxygen. We're just putting an ethyl group on it. Where in the Fischer esterification, we switched out the oxygens. C, what else can we do with carboxylic acids? We can convert them to acid anhydrides. Acid anhydrides, or just typically called an anhydride. And this is an anhydride. An anhydride is, if this was an H, that would be a carboxylic acid. If it was an ethyl or something, it would be an ester. But if we add another carbonyl, like this is an acid anhydride. I think it's the first time we've ever seen this functional group. It was not on our functional group list in Organic 1. Okay? Oxygen bonded to 2 carbonyls. We'll talk about where the term anhydride comes from. These R groups can be the same or different. When they're different, it's called a mixed anhydride. You could also call it a symmetrical or non-symmetrical anhydride. Because if they're the same, this is symmetrical. If they're different, it's non-symmetrical or asymmetrical. But very commonly, this is called, when they're different, it's called a mixed anhydride. And this would be a mixed anhydride, a phenyl on one side, a methyl on the other. Okay? How can we make mixed anhydrides? Base. What's base going to do? Same thing as above. Can I just show this deprotonated? Okay, can I just show that? We've already done that once. Now, just come in with an acid. What is that? An acid chloride? Okay. And the nucleophile will react here. By the way, we need to go back to the we need to jump over to the green The green is going to be a kind of a general discussion of reactivity. Sometimes we could do this first and then that. We need to get back over there though. Talking about how this is very reactive, very electrophilic. A nucleophile, and then this can add here. When we add here, okay, what do we do? Do we kick the chlorine off directly? See, at this point, we're starting to see common themes over and over and over, which I've already tried to get you to see, starting week 1. And week 1, we said this: when a nucleophile adds to this, we're going to break the sigma bond to chlorine or the pi bond to oxygen.
The pi bond.
Okay? That's one common theme. All right? Proton transfer, another common theme. And what does this give? Oxygen is now bonded to carbon and electrons up. And we have a chlorine and a methyl on the carbon. Yeah? So that was nucleophilic addition. This is so straightforward. What's next? Just one more step, we were home. Make pi bond, you kick off. There you go. And that gives what? Gives product. And what do you want to call that second step here in this? Nucleophilic addition followed by elimination. Overall, it was a substitution reaction. Under my hand used to be what? It's turned around now, isn't it? It's a methyl carbonyl. It's an acyl group. Acyl chloride. Under my hand used to be chlorine. Now it is oxygen. Substitution. It's a nucleophilic addition, elimination. Not SN1 or SN2. Anything really new there? You should have been able to predict this product without me even showing it to you. The only thing I would have had to tell you is, hey, what you just made is called a mixed anhydride. Number 3, chemistry of acid chlorides. Before we do that, though, I think we should go over to the green and look at some of the general discussion. And a little bit of what we just did. The mechanism we just did is called nucleophilic acyl substitution. It's an addition elimination mechanism for an overall substitution. Okay, not SN1 or SN2, addition elimination. Mechanism. Nucleophile, very generic, typically has a long pair, yeah. Acid carbonyl. Now, sometimes we will protonate the carbonyl first. Didn't we do that in Fischer Esterification? We protonated the carbonyl first. You're only going to do that under what conditions, though? Acidic conditions. Not under basic conditions. Addition to the carbonyl, electrons up, okay? Break the pi bond. This is your slow rate determining step. Okay? Form this, and we just formed it. I just erased it. And in that mechanism. It's called a tetrahedral intermediate because the carbonyl carbon is now tetrahedral. Then we come back and we eliminate some other group. That's going to be the fast step. And we reformed carbonyl, and the other group got kicked off. I'm not keeping track of charge here. It's too generic to keep track of charge. Reaction coordinate diagram, yeah, that should be more of an energy well instead of a point, right? More of a well. Right? One tetrahedral intermediate is a single intermediate. Now, this general description here does not include proton. If you have a protonation step or a deprotonation step, that's going to be extra steps and additional intermediates. So I'm doing this under neutral conditions. Now, which step does the leaving group leave in? The rate determining step or the fast step?
The fast step.
Fast. Because of that, leaving group ability is not as important as SN1 and SN2. In those mechanisms, the leaving group leaves in the rate determining step. Nucleophilic acyl substitution is a lot like nucleophilic aromatic substitution. When we did that, NAS, aromatic substitution, not acyl, what was the requirement for NAS? For that leaving group to be substituted?
Needs to have an electron drawn off the planet.
Yes, and that allowed us to do what in the mechanism? It allowed us to put the negative charge on a more electronegative atom by resonance. Whenever you do a nucleophilic addition to a pi bond, the negative charge needs to end up on a more electronegative atom, or it won't happen, either directly or by resonance. Where does it end up here at? On an oxygen, a more electronegative atom. Okay? But directly, we don't have to do resonance to get it there. So that's a consistency. And just like NAS for aromatics, then the fast step you lose the leaving group. Yes, then the fast step. This mechanism is very analogous. They're both called NAS. One's called aromatic substitution, this one's called acyl substitution. They're very similar though. You just don't have as much, you just don't have the resonance that you do when you do the aromatic substitution. Okay. In SN1, SN2, leaving groups are these halogens, tosylate, yeah? Okay. Iodine being best. In this mechanism, NAS, the leaving group can be a variety of things, other things. Oxygens, nitrogens, sometimes even carbon. Even carbon can be a leaving group from this if it leaves in the fast step. Now, it's not going to be a plain carbon. It will be stabilized somehow, but when we see the haloform reaction, we'll see if carbon has a leaving group in this fast step. That'll be in a month or so. Now, a standard like alkyl or H will not leave. But you will see a variety of things. If you've ever seen it be a minus, it can leave in a fast step. That's a bit different than SN1, SN2, right? SN1, SN2, you have stricter leaving group requirements. Reactivity of acid derivatives. Towards nucleophiles. Acid chlorides are the most reactive. Then what? What is this here? Then an anhydride. Then an ester. Then an amide, carboxamide, amide, amide. I call it amides. Least reactive. Why? Why this trend? Well, the acid chloride is most reactive because First off, they all have carbonyls. They've all got that pooling leaving this partial positive. But this one has a chlorine. And because it's so electronegative, it pools there. And so this is very partial positive. You got the oxygen and the chlorine both pooling. Let's skip this one for now. Go over here. Again, they all have the carbonyl, so let's just ignore that dipole. This one has oxygen instead of chlorine. Is the oxygen... So the chlorine is a net withdrawing group. What is the oxygen here? Does it withdraw or donate?
It donates.
It withdraws inductively, but it donates by resonance. And when oxygen can do both, which one does it do more? Just like in substituent effects, it donates more. Okay? Chlorine is a net withdrawer. This is the same as substituent effects for aromatics. So any partial plus that's here because of this dipole is kind of quenched by this donating. Now, what about nitrogen? It withdraws inductively. Not as much as oxygen. It's not as electronegative. Nitrogen also donates more. Why is nitrogen willing to donate more? Because it's less electronegative. Oxygen's more greedy. But it will donate. Let's look at the anhydrides. Why is the anhydride more reactive here? First off, anhydrides have two carbonyls, but only one of them is attached. Okay? The other, and let's just say this one, if it's symmetrical, then they're the same. You can attack either one. There's no choice. But I'm going to choose over here. This here is the leaving group. All that is the leaving group, just like over here, the chlorine is the leaving group. So one you attack, the other O carbonyl is going to be the leaving group. So let's look at here. Which carbonyl is more reactive? Well, that's a donator. What about this oxygen? Does it donate as much?
No.
Why not?
It's donating to
Because it's busy donating this way. So this oxygen, which is not donating that way by resonance, donates more this way. And when I say CO, I'm talking about the one we're attacking. Thus, that's why an anhydride carbonyl is more reactive, more electrophilic than an ester carbonyl. Now, we will also see this. These two will react with pure water. These typically do not. So there's a big divide right here. These are reactive enough to react with pure water. These require something stronger. like hydroxide, stronger nucleophile, or an acid catalyst. Since these react with pure water, do you think you find these in nature, where it rains?
Well, no, because they would ionize.
Right. Typically, you think you find these in the body, which is aqueous phase. Right. These two are typically not found in nature, not going to be found in the body. They're too reactive. These two tend to be reagents in the lab. Okay? Intermediates, reagents. They don't tend to be final products. You're not going to find these in a natural product. You're not going to find these in like a drug structure. They're reactive intermediate. These tend to be more end products. They're stable enough to exist in the environment or in the body. That doesn't mean we can't react them. They can be hydrolyzed. Okay? So here's your divide here. All right. This I see I already had here. Okay? We do resonance here. So you get this here. And this oxygen is now pooling. And that's here. You're not going to be able to do that here. But this oxygen pooling is still not as withdrawing as chlorine is. So that's why it's here. I showed a good bit of this below. Okay. The amide is a strong donator. Okay, you can do this with ester as well, but nitrogen really likes to do it. Nitrogen doesn't mind becoming positive. Strong donation. And so this is really not a carbonyl over here. It's not a donation. Of course, you can still react amides, but we see that it's got a tendency to be like this. And I can actually give you some NMR evidence for this, for resonance. This strong donation. Look at this compound, which is called this is a carboxylic acid with no other carbon. If this was a methyl, that would be acetic acid. You might know the name of this, it's just H here. Formic acid. You find it in ants, formica. Okay? Formic acid. If you make this an amide, that's called formamide. Formamide. If you put methyls here, that's called dimethyl formamide. DMF. A solvent we use in lab. Okay? That's DMF. DMF. Resonance here. NMR. I think we're about out of time here. How many signals would you expect here for NMR? These methyls.
They're equivalent, so it should be 1, right?
Why 1?
Because they're equivalent ages. So there'd be
They're
6
equivalent?
that are like.
You think they're equivalent? Yeah, that's reasonable. But if you look over at the NMR of DMF, we actually see they're not equivalent. 2 different signals for the methyls. Why are they not equivalent? That's because this resonance structure here is a major contributor. There's lots of double bond character here, and that's going to keep this from rotating. Now, one methyl is cis to the oxygen, the other methyl is trans. Okay? They're only equivalent if there's free rotation.
Okay.
Is there free rotation here? Like should be. It's actually not. Why? Because of resonance. Resonance gives you high bond character between the two. Resonance restricts the rotation, makes the methyls not equivalent. We see evidence of that in the NMR. Okay? Electron donation from the nitrogen into the carbonyl is a important thing. We'll see consequences of that later on. We're off on Friday, yeah? Okay, we'll hit the ground running on Monday. Have a good day, guys.